So welcome to lecture 17 of our CS2 classes. And remember what we did in the previous lecture was, first of all, we tried to have a look at, the compound binomial distribution and compound negative binomial distribution. And again, you guys do try to derive the skewness for the compound negative binomial distribution as well, just for a practice. And next up, we started off with something very different, which is actually not that different. So we incorporated reinsurance treaties within our compound distributions purview. So what we saw was, let's say if we have proportional reinsurance, then our life is very easy. So for the aggregate claim amount for the ceding company, it's just alpha times ds, and where my alpha is just the proportion limit of the ceding company, and 1 minus alpha is the proportion of xi which goes with the reinsurance company. So my SR is just 1 minus alpha s, and thus are my expectations as well. And whenever I have to figure out the MGF for my y, which will eventually help me to figure out my MGF for SI and SR, what I'm going to do is I'm just going to replace my y with alpha times x. And then, because I know that my x is a random variable, but my alpha, it is just another constant. So I'm going to write T alpha as some constant, and this would be a MGF of x. So I hope this is clear to everyone. And the next thing that we tried to have a look at was the case wherein we have excess of loss treaty in place. So let us say we have excess of loss treaty in place, and these will be the distributions for y and for z respectively, right? So now if I have to figure out my SR, or let's say if I have to figure out my SI, okay, so maybe give me another 2 minutes actually. Yeah. So now if I have to figure out my SR and SI, what am I going to do? What am I going to need specifically to figure out these? So again, I can rewrite my SI like in the previous case as just summations of yi's, right? So again, I know that my yi will either take whatever value my x has, or it will take the value of m, right? It will never take a value higher than m. And for SR, I'll have, so I know that this has a restriction and it takes values from 0 till m, right? And now if I have to write my SR, what will I have? I have Z1 plus Z2 up until Zn. And what are the values that my Zn can take? Anyone? What should I write here for the domain of Z? So what will be the values that my Z can take? Okay, let's start with what is the minimum value that a reinsurance company might have to pay.
X minus m, right? If x is greater than m.
Yeah, but I want in terms of numbers, right? So here what I wrote was
So
y,
0.
0, right? It can take 0 value. And what will be the maximum value that this Z variable can take?
That only, right? X minus m.
Yeah, so for my x minus m, I mean, my x can essentially go on till infinity, right? So my x minus m would be, in theory, going till infinity. So I know that my z can take values 0 till infinite. But again, if you have a look here, what's happening with the reinsurance guy is that we are taking into account the cases where it has nothing to do with the claims, right? Basically, where it incurs a claim amount of 0. So it basically distorts the distribution as well, and it's just not convenient because not every time the reinsurer will be informed that there was a claim, but you guys don't have to play any part with incurring it. So they will only be caring about the claims for which they have something to do with, right? So remember, in the previous cases, what did we do? We defined another random variable w, right? So what we did was we defined a random variable w, which was z conditioned upon the fact that the claim amount indeed exceeds the value of the retention limit, which is when the insurance will come into picture, right? So now I will define another random variable, which is sw, and that would be summations of w's. So it would be w1 plus w2 up until, what should be my subscript here? Anyone? What should be my subscript here? Will it be n? Can I write n here? So again, remember what we are now trying to do is, so what first, when we started off with today, what we had a look at was z's and we had y's. And this went all till n. So this is indeed the total number of claims that you observe, right, as an insurance company. You have n number of claims which you have observed. And so you have n number of Zs for the reinsurance company as well. But we know that some of these Zs are going to be 0, where the x is just less than or equal to m. So the insurance company might not know about those claims always. So what we do is we define another random variable w, like we did in the reinsurance chapter, and then we define aggregate claim amount. The actual aggregate claim, I mean, this SW is going to be equal to SR, right? Because these values, let's say if these are 0, it won't really add up to any amount. It will still be 0. So this SR is still going to be equal to SW, but it's just a convenient notation, a very efficient manner of representing things. So the number of W's will be the number of non-zero claims that I have for the reinsurance company, right? So let me denote those non-zero claims. So this is, let's say, my NR, which denotes the number of non-zero claims to the reinsurance company. Okay, so what I have done is, instead of n, I have just defined another random variable nr, which measures how many claims do I have for the reinsurance company which aren't 0. So basically, the actual number of claims for the reinsurance company. Is this clear to everyone? Does this make sense? Hello, do I have you all?
Yes, ma'am.
All right. So now again, we'll try to figure out the moments of SW, right? So now let's say if I have to figure out expectation for SW, what will it be? Anyone? How should I write my expectation of SW? So previously, what did we have? We had S equals to x1 plus x2 up until xn, right? And what we did was we wrote that our expectation of S is equal to expectation of x, which was the severity of the claims, times the average frequency of the claims, which is expectation of n, right? So how can I use that to write my expectation of SW now?
Expectation of NR into expectation of W.
Thank you very much, Mihir. So yes, it would indeed be expectation of NR times the expectation of W, right? So now what we have to do is figure out expectation of NR and expectation of W, right? So let us have a look at how to do that. So now the very first thing, okay, let me just say that my n follows a Poisson distribution with some parameter lambda. Okay, so I know that in general, if I'm looking at just S, it will be compound Poisson, right? And my expectation of S is just going to be expectation of n times the expectation of x, which will again just be lambda times m1. And my, does anyone remember what was the variance of S here? If I am looking at a compound Poisson distribution?
Lambda
What?
n2.
Exactly. So it was lambda times variance of X, right? Okay. So now we have to define, so now what we have to do is we have to figure out the expectation of NR and somehow the variance of NR as well, if we can, right? So that we can use it to write our expectation of SW and maybe the variance of SW. So again, now if I just use the fact, yeah, so now I'm going to use the fact that my N follows Poisson distribution with the parameter lambda. Okay, so how can this help me to determine something about NR? So just reminding ourselves, N, capital N, here represents the total number of claims that we observed, and NR represents the number of non-zero claims for the reinsurance company, right? So one way to do this is actually to use a dummy variable. So what you do is you write that NR is nothing but just additions of I1 plus I2 up until IN. And you define your I's as taking a value of 1 if your X value exceeds the value of M and 0 if it does not. So essentially, what you are doing is, we know that our n is just going to take values like 0, 1, 2, 3, right? And so is our nr going to take values. So what I am doing is, I have rewritten nr in terms of some random variable which I'm adding up n number of times, and what I say is that this random variable takes the value 1 if my x is greater than m, and this random variable takes the value 0 otherwise. So my NR essentially is now just a summation of IIs, right? Where I takes value from 1 to capital N. Does this make sense to everyone?
Yes, ma'am, but can't we use truncated Poisson distribution?
Yeah, so the thing is that you can indeed use truncated distribution as well. But again, what will happen is whenever you try to figure out the probabilities of these things observed, so as of now, what happens is this renders everything easier because it's a dummy variable. I is taking the values 1 or 0, right? So if you use truncated distribution, then it becomes increasingly complex later on, I would say, to also figure out the MGF. And because you'll have to use, so let's say if you want to figure out the MGF of NR, sorry, let's say if you have to figure out the MGF of SW. Okay, so what will be my MGF of SW here? It will be MGF of NR, right? With log of MWT here, right? So it would be really difficult to figure out the MGF of NR if you take some truncated distribution or something else. Does this make some sense?
Yes, ma'am.
Okay. So now what we have to do is, so what I have said is that my II takes value either 1 or 0, right? And so my NR is again just the addition of all of these IIs. All right. But again, I want to define something else as well. So what I care about is now expectation of NR, which is here, right? So now if I have to figure out my expectation of NR, how can I write my expectation of NR? Anyone? How should I write my expectation of NR? Given that NR is a sum of these IIs. Anyone? So again, we'll actually be using the fact that it is a sum of some random variables to determine the expectation in the similar way we did here. So what should I write here for my expectation of NR? Anyone? Just try to guess. I'm not saying you guys do have to, give the correct answer. What does your intuition say? Yes.
Expectation of N into expectation of I.
Exactly. I mean, it does make sense, right? So I have expectation of I times the expectation of N. So I'm adding up I random variables N times, which is kind of similar to adding up X's N times. And that would render S here. So I would have expectation of S as expectation of X times the expectation of N. So here I have NR and I'm looking at the random variables I. But again, do we know anything about I? So I only know that my II takes two values, either 1 or 0, and depending on whether my X is greater than M or otherwise. So the very first thing that I now care about is to figure out expectation of NR, which is in a way going to help me to figure out my expectation of SW, which is my end goal here. So I need to figure out expectation of I. And how can I do that? So do we know what distribution I follows? Would you guys want to guess what should be the distribution for I here?
Is it Bernoulli?
Is it Bernoulli? So Bernoulli with what parameter? We need some parameters as well, right? And also, why do you think it should be Bernoulli and not binomial? And what about others? What do you guys think?
Ma'am, will it be binomial with probability so P will be probability X greater than 0?
Okay. And what should I write here? The another parameter. Binomial has two parameters, right?
Yes.
So the other parameter represents a number, right?
But I think we are considering individual I's, right? So individual I would follow Bernoulli because there are only two outcomes, and I think there's only uh, one case that we are taking, but the addition would lead to binary.
Exactly. That was indeed a very great observation, Vanshita. Thank you very much, and indeed a correct one as well. So what I'm going to define here is what I meant by this I was some only one particular I. So let us say that the probability that I observe my x value greater than m is defined by pi. Okay, so I will have my I following Bernoulli with pi, right? Does this make sense? So now I can easily figure out the expectation as well for my I variable. And again, whenever I'm seeing that this is the probability that my x takes a value greater than m, it also implies that this is the probability that my I takes a value 1. And we know that there is only a binary choice for I random variable. So it's going to be that my probability that I will take a value of 0, which is the only other value it can ever take, is going to be 1 minus I. Right? Does this make sense to everyone? So now you can easily figure out the expectation of NR, which would just be the expectation of I times the expectation of N. So we know the distribution of I, we know the distribution of N as well, right? So we are done with that. And then I guess the similar thing you can do with the variance as well. So for the variance of I, you do now know the distribution of I, right? So it takes the value 1 and 0. So if you want variance, you can easily figure out expectation of x square. So the expectation of I square as well, right? It would just be equal to the expectation of x because I takes values only 1 and 0, and 1 square is 1 and 0 square is also 0. So it would just be equal to the expectation of I. Is this clear with everyone? What about others? Any doubts? Any queries? So again, we have to be mindful of the assumptions we are going to make. So here when I'm writing my IIs, I am making assumption that all of my IIs are IID. So they are not only independent, but they are also identically distributed. So that is one assumption that I'm going to make. Okay. And we know that, for practical purposes, we have to use this because not every time the insurance company will get to know information about all the claims. So it's most of the time just the case that they will know if at all they have anything to do with the claim amount. And that would be the case wherein always they will have to pay a certain amount. I mean, that is actually what happens with the insurance company as well. So the number of policies is never equal to the number of claims, right? Because there won't be a claim on each and every policy. So we write summations only up until capital N, and capital N is the number of claims that the insurance company has incurred. So we do the same thing with the insurance company as well, where I'm denoting NR as the number of non-zero claims for the insurance company. So that is a new random variable that I have now defined for my convenience. And again, to figure out its expectation, I have to, because I really do not know much about NR as such, what I do is I use the information about N and try to sneak it in to see and correlate, and not exactly correlate, but relate it to R so that I can figure out the moments of NR as well. And what I do is I instead use a dummy variable. So, okay, so whenever I talk about dummy variables, what I did here was I took 1 for x greater than n and 0 otherwise. Can I do the opposite? So can I take 0 here and 1 here? What will happen if I take 0 here? So if I say that my II will be 0 if my x is greater than m, and it will be 1 otherwise, then what will happen? Will it still work?
I think yes, because the distribution remains the same.
Okay, so the distribution remains the same. Let us see what happens. So what I said was, I'll just erase this 0, 1. And what I'll write here instead is 0 up and 1 here, right? Okay, so again, I'm going to keep everything same. So Vanshita says that it will still work. So Vanshita, can you tell me if I put 0 for every time I observe my claim amount greater than M and 1 for the rest of the times, what will my NR represent here?
Okay, it will represent all the claims where the zero claims to the insurance company, not the non.
Exactly right. So it would represent all the claims where only the direct insurance company has to come into picture. There is no play of reinsurance. But again, what we are trying to care about is now the reinsurance company, right? So we are looking at SR and R. So I mean SW, sorry, which is actually equal to SR. But yeah. So again, we cannot do this 0, 1. Okay. So we have to keep it 1, 0 only. So that whenever I'm writing 1, I'm actually adding up every time my reinsurance company has to pay some amount. Does this make sense to everyone? Is everyone awake? Anyways, thank you very much, Manshita, for participating in the discussion. All right. So now let us try to move on and see if we can figure out the MGF of our SW, right? Because that is the ultimate goal of ours, to know something about SW, to know the moments of SW, right? So now what I'm going to do is, let me just again rewrite that my NR is I1, and this goes on up until I capital N. So again, remember, we're still looking at collective risk models where my N is indeed a random variable, which I maybe know the distribution of, but I just don't know the actual value at a time. And okay, so we did write the formula for MSW, right? So to figure out MSW, we need M of NR. We need the MGF of NR as well. So what do you guys think the MGF of NR will be? I mean, it will obviously depend on the distribution that my NR has, right? So what do you guys think is the distribution of NR here?
Binomial.
Binomial. And with what parameters?
I and N, capital N.
I and capital N. Okay, that's really good, guys. What about others? What do you guys think it should be?
Same, ma'am. Capital N pi.
Thank you, Mir. And what about the rest of you guys? What do you guys think?
Same, ma'am.
Same
Binomial.
for everyone? Okay. So let me, I guess this is it just looks a bit confusing. So let me remind you guys, what we previously did was, so we had x1 plus x2 up until xn. Okay, so now if I say, and this was equal to s, and if my n had pos1 with lambda and my x had gamma distribution with some alpha and some lambda, what happened to s? What was my distribution for s?
Approximated it to normal.
So what was my distribution of s? Did it take the distribution of x or did it take the distribution of n? So it was something like compound pos1, right? Do I have everyone? So this is the very first case, I mean the very first thing that we studied in this chapter, right? So again, reminding ourselves, Oswa here was the distribution that was for the n here, and we had compound. Why? Because our x is continuous and our n was discrete, right? But what happens here? Is my I continuous or is it discrete? Anyone?
Discrete, right?
It is discrete, right? And what is my n? N is still possible with the parameter lambda, right? So again, it is still discrete, right? So we cannot necessarily say that it's going to be a compound distribution something, but we still don't know what it's going to be. So by having a first look at this and seeing some commonalities, except the fact that it's not going to be compound because this is not continuous anymore. What we can say is this. I mean, if you don't recall these facts again, it's very plausible to say that this should follow binomial, right? Because we see that it is addition of the Bernoullis, and we think that addition of Bernoullis, then it's going to be binomial, right? But again, we have to remember that it is not any addition of Bernoullis. We do not know the number of additions we are doing here. Had we known, let's say if we had small n here, then it would have been binomial. But now we do not know, as of now, we have no idea of this n here. So what we'll have to do is, let us try to figure out the distribution for R and R. And the very first thing that comes to at least my mind whenever I have to figure out a distribution of some random variable by myself is use MGF. because we know that there is a direct link and a unique property that each MGF corresponds to a unique CDF, right? There is no duplicacy going on over there. So now let us try to figure out my MGF of NR. So I have to figure out MGF of NR. So again, using the actual formula, I'm just going to write it as TNR. And remember, my NR is one random variable. It's not two different random variables. NR is just one random variable. Okay. So what should I be doing next? Anyone?
Write NR as I1 plus I2 till IN.
Okay, so I'll have T here and I can write it as I1 plus I2 up until IN. And what should I be doing next? So we have to remember the fact that my I's or J's are IID, right? Yeah. So what should I be doing next?
Then we can split it out, like expected value of e raised to t times I1 into e raised to expected value of e raised to t times I2 till IN.
Okay. Then what should I be doing? I can maybe just summarize it as pi I going from 1 to capital N. Expectation of e raised to t I small I, right? And what would this be?
Since they're identical, it will just be yeah. So this will be MIT, right?
Yes.
And then the whole thing will be MIT raised to N.
So how many of you guys agree with what we just derived? Vanshit, I couldn't hear you well.
I do agree.
Okay. What about others? Do I have you guys? Prazika, what do you think about this? Savi?
Yes, ma'am, I agree.
You agree? Okay.
Ma'am, I think only I, capital I should be there, right? Because they are identical.
Okay, yeah, I mean, it's all right because so why I have written I small I is because we necessarily do not know what is capital I, right?
Okay.
I only have I1, I2 till IN. So yeah, it's fine. Anything else? Should I write a small n here or a capital N there?
Capital N.
Capital N. Okay, but my capital N is a random variable, right? So what am I doing is I'm raising my MIT to a random variable. Does this make some sense? Or, I mean, can you do that? So maybe
No, it has to be a constant, right?
It has to be a constant, right? So where did we mistake in how come we ended up with a random variable in the power? That doesn't seem right, right? So maybe let me take you guys back to, oh, so it's not here. So I think you guys must have it in your books, right? Go back to the steps where we derived the NGF for S for the very first time. What did we do? There was a special law that we tried to use to even figure out its expectation, to figure out its variance, and so did we use it to figure out its MGF as well. So what was the thing that we used? What
The
was the one?
iterative thing.
Exactly, right? We use the law of iterative expectations. So maybe if we use that, we can write that, my capital N takes some particular value and then take another expectation for that. So let me just discard all of this for now. So I don't think this really makes any sense. So what I'm going to do is maybe try to do something else. So now Isha says that maybe I should try to use law of iterated expectations. So what I'm going to do is I'm going to first write expectation, and again this would be with respect to NR, okay, and this will be my expectation. Okay, so it's not going to be with respect to NR. Let's see. So I have expectation of e raised to TNR, and what I'm doing is I'm assuming that my n takes a particular value which I have observed as small n. So this is my first expectation which I have now conditioned upon the value of n. So now here I'm going to write it. Write that I'm going to take expectation with respect to capital N. Okay. Is this step clear to everyone? This is very important. So we have used law of iterated expectations here. Any doubts with what I have written on the board?
Why have you written N in the subscript with the first T?
Okay, so again, remember what I have conditioned upon. I have conditioned from a value of capital N, right? Because that is where we got stuck, right? We didn't have an R here. We had capital N, right? So we want to do away with this capital N. So what I have done is I have taken its value as small n, and whatever I condition this upon will be what's going to come out here, expectation with respect to n. I mean, that is what the law says always.
Okay, got it.
Right? So generally what happens is you don't have anything here, right? So it's just the unconditional expectation. But now remember, that is the expectation of n. So again, moving forward with this, now we know the value that my n is going to take, right? So what do I have? I will write expectation of n again here. And now what can I do here? Anyone? So if I know my value of capital N, this will just be again the same thing that we did here. So now this would make sense because instead of capital N, we are going to have small n here. So what do I have? I have expectation of T times. Instead of NR, I'm just going to write whole I expansion, right, till IN. And given that my n takes a value small n, right? And now because I know what value my n takes, I'm going to incorporate this in here. So I'll have expectation of e raised to ti1 times expectation of e raised to ti2 and so on till expectation of ti small n. Does this make sense to everyone? So remember this bracket corresponds to this bracket, okay? Can I have a round of yes or no if you have understood this step or not?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So I've essentially done the same thing, right? The only part where I got stuck here was that I had a random variable in the power. And now I have conditioned upon that random variable itself so that I don't get that in the power. So again, I'm just going to use the same steps here again to write this as pi I going from 1 till small n, expectation of e raised to t I, right? So what will I have? I have expectation of n. And then what do I have here? This will just be MIIT, right, raised to small n, right? Okay, so now what do you guys think this amounts to? So again, remember, I'm taking expectation of all of these things. What can I do here now? Anyone? So remember, we have to determine the MGF so that we can see to which distributions MGF it looks alike to, right? So I can't really work with expectation still in there. Sorry. Oh my God. Yeah, I'm really sorry if that was terrible for your ears. Okay, so again, back to our studies. What were we doing here? What can I do here to which will give me something that I can compare with what I have in the table booklets? Anyone? Yes. Okay, so there's actually a bit of a trick that I'm going to use here, and we aren't quite done yet. So what we have here is expectation with respect to n of MIT raised to n, right? So the very first thing that comes to my mind is, maybe because I know this from prior experience, is that I should be taking E and log. So what I do is I write my expectation as it is and I rewrite this. If I have MIT raised to n, I can rewrite this thing as E raised to n times log of MIT. Does everyone agree with this?
Yes, ma'am.
Yes. So I'm going to use that fact. Maybe I can put it in a different color. And it's going to put everything in different color. Okay. So what I have here is, so I'm going to use this fact here. And what I'll have in here will be e raised to n log of MIT, right? So now how does this look like? Can you summarize this again for me? Anyone? So I have e raised to n, which is a constant, and then I have log MIT, and this is expectation of n.
Will it be mn of log MIT?
Looks like it, right? So what I'm going to have here is, because this is expectation, I mean, so again, reminding ourselves of what we had was, so I wrote that, my capital N takes a value small n. But what if I didn't specifically wrote what value my small n took, what value my capital N took, right? So what will I have? So what will I have here is not this, right? And then I won't have this as well. And then maybe here instead of small n, I will just write it as a capital N, right? And then here also I'm going to write it as capital N. Here also I'm going to write a capital N, and then here also I'll get one capital N, right? So again, reminding ourselves, we know the value that capital N takes, and but still it is random variable because we're taking expectation with respect to capital N, right? So what I get here is MGF of capital N at log of MIT. Does this make sense to everyone? Oh, and I think I forgot a little something here. It's not just small I, it's a capital I. Okay. Do I have everyone? I'm audible, right?
Yes, ma'am.
Okay, so now that I have, so, okay, so what we started off with was MGF of NR, and we saw that it is indeed just the MGF of N at log of MIT. I mean, this is what we have always seen as yet, right? Always for compound distribution, but here it's just that NR is, it doesn't have the name compound, but it still has MGF, which looks a bit like one that a compound distribution would have. Okay, so what I had in the previous slide was MGF of NR at T is what? It is MN log of MIT, right? Okay, so what should be my next step now? I'll have to somehow figure out my MGF of I as well, right? So do you guys remember what was the distribution for I? It was Bernoulli, right? And what is my Bernoulli distribution? It is just the binomial distribution with the parameter n equal to 1, right? So is it fine if I write my I as binomial 1 comma pi? Does it work? Right? So now what will be my MIT? Anyone? So look at the table booklet and page number 6. Because we don't have the MGF and expectation and everything for Bernoulli, right? So what I did was I just rewrote Bernoulli as binomial with n equals to 1. And now I'm going to use binomial distributions description and substitute n equals to 1 everywhere, right? So my MIT, my MT generally is q plus p e raised to t raised to n. So what I will have here is my q is 1 minus pi and my p is pi and this will be e raised to t and a raised to n. So n is going to be just 1, right? Does this make sense?
Yes.
Yes. Okay. So that is my MIT now. But again, let us try to have the next step for this. So now I know what my MIT is. And do I know my MGF for n? What is the distribution of my capital N here? Anyone? So to figure out the MGF for my capital N, what do I have to do? Do I have to derive it again? Or do I know the distribution of N and I can maybe see it in the table booklets? What do you guys think? Con, I guess this really shouldn't take time, right? Do you guys remember what is my capital N? Have I defined somewhere my capital N? Yes. So what is my MNT here? Do you guys have your table booklets with you?
E raised to lambda into e raised to t minus 1.
Exactly. And who was that speaking?
Savri.
Savri. Very good. Thank you very much. So what will it be? It will just be e raised to lambda times e raised to t minus 1, right? But now what do I have? Instead of t here within the brackets, what do I have? I have log of MIT, right? So what I'll have to do is I'll have to substitute instead of t here, log of MIT. So again, maybe we can go through it step by step. So what I'll write here is e raised to lambda, e raised to, and instead of t, I'm gonna write log of MIT and minus 1, right? But now again, if I have e and log, it will just get cancelled. So I have e raised to lambda MIT minus 1, right? And I do know that my value for this MIT is nothing but just this, right? So I'll just substitute that now here. So what do I get? I get e raised to lambda times 1 minus pi plus pi e raised to t minus 1, and this is also a 1. So 1 minus 1 will eventually get cancelled, and what you're left with is e raised to lambda times pi e raised to t minus pi, and maybe we can take this pi outside. So what you'll be left with is e raised to t minus 1. Okay, and remember, what is this? This is my MNR of t. So now I don't have any random variables and nothing, right? So what does this look like? Anyone? Does this look similar to any of the MGFs?
Poisson distribution.
Poisson distribution with what parameters?
Lambda into pi.
Exactly right. So my NR follows Poisson distribution with the parameters lambda times pi. So this is the result. This is a very, very important result. And again, reminding ourselves, what is my NR? It denotes the actual number of non-zero payments that will be made by the reinsurance company, right? And IJ is just another indicator random variable, a dummy random variable, which takes the value of 1 if the reinsurer makes a non-zero payment on that one particular claim, right? And it will take the value of 0 otherwise. So what we just derived through the MGF is the distribution that my NR follows. So the distribution of my NR is POSVA with the parameter lambda pi, right? Okay, so remember, when were we trying to use NR, and why did we even require the distribution of NR to be known in the first place? So we kind of did a lot in between, but yet here we are, right? We will use the expectation of NR, we will use the distribution of NR to figure out the value of expectation of NR, right? And what do I have here? Expectation of SW. So now if you have a look, NR is just another random variable which replaces my N here. So previously my N used to follow POSVA with the parameter lambda, right? When I had x1 plus x2 up until xn. And then my S followed compound POSVA with what parameter? Lambda again, right? So now if I have a look at this distribution, what do I see? I see that my NR follows again POSVA distribution, but with the parameter lambda pi, right? So now if I have to figure out my expectation of SW, now let us try to figure out its expectation, variance, and everything else. Because we know stuff about NR and we know stuff about W. Oh, sorry, we don't know yet the stuff about W, right? So do you guys remember anything about W? Anything that we studied which could have which could be helpful to us here. So, okay, maybe what we can do is, like always, we'll ignore W for now, and we'll do a sum wherein we'll see how to incorporate W once we know the distribution and everything else about it. So let us just try to figure out expectation of S. So now I'm gonna write expectation of SR. So, okay, we do know that my NR now follows some POSVA distribution with this parameter lambda pi, okay? And my expectation of SR, as previously written, was expectation of NR times expectation of W, right? So my expectation of NR will just be lambda pi, and I'm just gonna write this as expectation of W, as it is. Does this make sense to everyone? Yes or no? Does this make sense? So remember, I have done really nothing new. So what we did was, we have already written this, right? That my SW is nothing but SR. So my expectation of SW is just expectation of NR times the expectation of W. And what we did was, we just derived the MGF of NR, which led us to the conclusion that my NR follows POSVA with the parameters lambda pi. And now I have used that fact, and again I've also used the fact that my expectation of SW. Okay, so my SW is just going to be SR, and that is nothing but lambda pi expectation of W. Is this clear with everyone? Can I have at least a yes or a no, if it's clear or not?
Yes.
Yes, ma'am.
Yes, ma'am.
Thank you very much. So let us now try to write the variance of the reinsurer's claim amounts. So the aggregate claim amount. So what will I have here is variance of SW. Okay, so what was the formula for the variance? Okay, so what I can do is, maybe let us write it in terms of all the expectations and everything else as well, right? So if I have to write the variance of SW, it was something like variance of W. Oops. So it was something like variance of W. Let's say, and this is a smaller W that I have, and here I'll have expectation of NR, okay, plus expectation of W times expectation of NR. Do you guys remember this formula? It's also given in the table booklet. So again, reminding ourselves, what is my expectation of NR here? It is just lambda times pi, right? And this I still don't know. So this is my variance of W plus. I again don't know the expectation of W, but I know the expectation of NR, which is again lambda pi. So I'll have expectation of W here as it is. So what I can do is, I can take lambda pi as common, and I will just write the variance of W within brackets added to the expectation of W. So this would in essence be the variance of SW. But again, this is really not what we like, right? We want to figure out the expectation of W, the variance of W as well. So let us see, what do we know about W? Do we know the distribution of W? Does anyone remember the distribution of W that we derived? Yes. So remember in the reinsurance chapter, we actually derived the distribution for W in terms of excess distribution. And what was it? So I also remember that it was somehow intuitive, right? So we defined W as X minus M such that my X takes a value greater than M. So if I were to write my F of W here, what would I have? Yes.
And is this the same W that we had before?
Yeah, it is the same W. So, okay, remind me, what was the W that we had before? What did it represent?
It represented the reinsurer's conditional distribution, right?
Right. And what does it represent here? And where? Can you tell me what does W represent here? And where? Can you hear me? Yes.
Yes, ma'am. I'm trying to figure it out.
Yeah. So maybe go through your notes and you will see what the distribution we wrote for W. And also just, it's fine if you just tell me in words, what does W represent here?
Ma'am, I'm not able to find it.
Okay, so can you just explain me what is W?
Ma'am, what I know is it's the conditional distribution of Z given X is greater than M.
Right? And what is my Z? Z is just X minus M, right?
Yes.
So
Yes.
remember, when we try to derive the distribution of W, we actually did a lot of steps, right? And we derived, and at the end, we did say that, it really seems intuitive because whenever I'm writing, let's say, so what is my F here? It just represents the probability that my random variable W is going to take a value which is small w, right? And if I know that my capital W is X minus M such that X is greater than M, do you guys remember what did we do? So what we wrote was something like this. Let's say we have capital W is equals to small w. Hope I'm audible, yes. So what I have here was, this would be equal to probability. So instead of capital W, what I'm going to write now is X minus M equal to small w such that my X is greater than M, right? And what we did here was, because my M was just a constant, we wrote that this is indeed equal to X taking a value W plus M upon X being greater than M's probability. So again, there would be an intersection here with the probability that X takes a value greater than M, right? We did something like this, and we actually derived that my F of W was nothing but F of X. And what will be my value of X if my W takes a value small w? It would just be small w plus M. And M is also just another constant upon the probability that I observe a value of X which is greater than M. It was 1 minus F of M. Does this ring a bell? So again, you don't necessarily have to, even remember stuff. Just remember the intuition and the way we derived it. And what does it try to say? So this F really looks complicated here. But what does a F represent? What does a PDF say? It is just a probability that my W is going to take some value, right? So I can summarize my F of W as such. And I think it's not maybe very much clear here as to how you're going to use this to figure out the expectation of W and the variance of W. So maybe we can do a little sum, and in that sum we'll actually calculate the value of expectation of W and the variance of W. So are you guys ready with book, paper and pen at least? I do hope so. So let me just write the specifics of this. Yes.
Ma'am, I think variance of SW, it should be expected value of W the whole square.
Expected value of W the whole square. Oh yeah, I think it should be that as well. Yeah, if I have made some errors in the formula, just ignore those, okay? I mean, I think you guys are better judge. And yeah, it's actually, it should be expectation of x square always, right? Yeah, thank you very much, Saudi. Yeah, very good observation. Okay, so what do we do next? I was gonna give you guys a sum, right? Okay, so what I have here is a little bit of information about n and x. Okay, yeah, so I know that my n here follows POSMA. So remember we had lambda. So instead of lambda, I now have its value, which is 10. And my x here follows a uniform distribution where my a is 0 and my b is 2000. Okay. And again, I'm looking at excess of loss. So my m is 1600 here. And what I have to do is I have to figure out the mean, the variance for my S value, okay? For my SR, SI, and Zs. So I have to basically figure out mean variance for my SR and SR. So so basically, how should I go forward to solving this? Anyone? So let us try to solve this sum together. So what should be my very first step? So remember, I have to figure out the mean, the average, on an average aggregate claim amount that the insurance company will have to incur, and the average claim amount that the insurance company will have to incur. And also I have to figure out the variances of those guys. So let us first start with the easiest thing, which is SI, right? SI is always easier. So what should I do? Anyone? What should be my very first step here? So take your time. Yes. So remember, the information that I have is that my n follows Poisson distribution with the parameter 10, and my claim amounts are uniformly distributed on 0 and 1000. And I have excess of loss treaty in place with the retention limit as 1600. And what we have to do is we have to figure out the mean and the variance of the insurers as well as the insurers aggregate claim amount. All right. So remember, not every time it will be given to you that, n follows POSWA 10. Maybe what they can tell you is that the aggregate claim amount, which is your S, follows compound POSWA distribution with the parameter 10. So from that also you can infer that if your S is compound POSWA, then you know that my N has to be POSWA. And if it follows compound POSWA with the parameter 10, then my N also follows POSWA with the parameter 10, right? So that's fine. But again, what should be my first step? So let us say I want to figure out the average claim amount for the insurance company, which is SI. right? So I have to figure out expectation of SI. So what should be my very first step here? Anyone?
Find out expectation of n and expectation of x, right?
Yeah, so I'll have to figure out expectation of n and expectation of x. So let us try to do that. Okay. So what is my expectation of n here? Anyone?
10.
10, right? And what is my expectation of x here? So what is the formula for the mean of a
1000.
uniform? 1000? Did someone say 1000?
Yes, ma'am.
Yeah, so it will be 1000, right? Okay. So now I have to figure out expectation of, sorry. Yeah, so now what I have to do is figure out my expectation of SI, right? Okay, so what can I do now? So you guys do know, right, that the expectation of uniform distribution is just half of 0 plus 2000. So it will just be 2000 upon 2, so it's 1000. And that's how you get that 1000 there. But yeah, what should be my next step? So to start with, have we defined our SI? So we do know that my S here is what? It is x1 plus x2, so and so up until xn. So if I were to write my SI, how can I write my SI? Anyone?
Y1 plus Y2 plus 1.
Exactly. So it will go on from y1 till yn, right? Okay, so now if I have to figure out expectation of SI, I am indeed trying to figure out expectation of this sum here, right? So now I know what I'm looking at when I say SI. So now if I have to write expectation of SI, how can I rewrite this as?
Expectation of y1 plus y2 up till yn.
Yes. Anything else that I can do? So remember, we can actually save ourselves all of the trouble of deriving that the expectation of SI is just going to be expectation of Y times the expectation of N, right? Because again, we'll be meeting with a random variable N here, so we'll have to use the law of iterated expectations and go through everything again just to derive this, right? So I'm going to use this directly here. And again, you can also use it directly. You need not sit and derive and take double expectations every single time, okay? So I'm just going to write this for now as equal to expectation of y times expectation of n. Okay, so I do know the expectation of n, but do I know expectation of y? Yes or no? Do I know the expectation of y?
We have
What
to.
do I know? We have to figure out, right? So what do I know about y? Do I know the distribution of y here? What is my distribution of y when I have excess of loss rate in place? So do you guys remember? What should I write here?
It will be X and then 1600.
Exactly. Thank you very much. So now if I have to figure out expectation of y, what would this be?
Integration of 0 to 1600 x fx dx plus integration 1600 to infinity m fx dx.
Does everyone understand this?
Yes, ma'am.
And do you agree with what I have written on the board here? So this is what? And this is my expectation of y. Okay, so now you will just have to solve for this. But again, what do we know about f of x? Do I know what is my f of x here? What is my f of x here? Anyone?
1 upon 2000.
1 upon 2000, right? Because my x, so if you try to have a look here, let's say this is 0 and if this is 2000, my uniform distribution is just gonna look something like this, right? And we say that each one of these is equally likely, so we just write here 1 upon 2000, and if you multiply 2000 you get a 1, which is the area under the curve, which always has to add up to 1, right? So that's good. And now if I have to figure out the probability that my x will take a value higher than 1600, how can I do that?
One minus 1600 minus 0 upon 2000 minus 0.
Yeah, I'm sorry, I missed what you said. What did you say?
1
I missed
minus
that.
1600 upon 2000.
Okay, so how many of you agree with this? Does this make sense?
Yes, ma'am.
Okay, so basically 1 minus 1600 is going to be some negative value, and when I
I'm
divide
1
that,
Have it
minus
1 minus.
1 minus 1600 upon 2000.
okay, yeah, that underline shouldn't be there, right? So what you did was 1 minus the f of x, right? So what I have here is probability that my x will take a value greater than 1600. So that will just be equal to 1 minus f of 1600, right? Which will be this. So what will this give me? 16 upon 20 is 0.8. right? You'll have 5 and 4 up there. So it's going to be something like 0.8. And here, I mean, I'm not going to do this integration and everything for you guys, but basically you can derive the answer for this, right? So it's going to be something like this. You'll have 0.0005 x square for this, again upon 2, and this would be from 0 till 1600. Plus, okay, this is 1600 and not 3 zeros. This is 2 zeros only. Plus 0.2 times 1600. And this will give you the answer as 960. Okay, so this is how you derive expectation of y. And now if you have to figure out expectation of y square, what will you do? You will just do x square here, and here you will have m square, right? And the rest of the stuff will be as it is. So I guess you guys can do that on your own as well. And that will eventually help you to figure out the variance of SR. So now that we know the expectation of y, let me just check once. Yeah, so okay, the accurate thing to write would be yi everywhere, but yeah, okay. So what I'm gonna do now is figure out the expectation of SI. So remember, what was my expectation of SI? It was just expectation of yi times the expectation of n. So what is my expectation of yi? It is 960, right? And what was my expectation of n? 10. So I get my answer as 9600. And again, I would say to figure out the variance of SI, what else do you need? So you need expectation of y square's value as well. And what you can do is figure out it by putting a square here and a square here and then calculating the expectation of yi square's value. And that you will get as 1194666.7. Okay, so and then if you try to figure out the variance of SI, what will it be? So what will be my formula for variance of SI? Anyone? Yeah. What will be my formula for the variance here?
A variance of y into expected value of n plus expected value of y the whole square into variance of n.
Yeah, and what is my variance of n and my expectation of n? It's the same, right? Because it is a Poisson distribution. So remember, whenever my n is a Poisson, and if I'm looking at compound Poisson distributions, my expectation is expectation of n times the expectation of y. And with my variance, what do I have? I'll be left with 10 here and the expectation of y square here, because eventually the expectation and the variance term, because they are the same, they'll cancel each other out. And this is the nice property always. So you get here lambda times expectation of. So if you go, if you look at your notes, we have derived, right, that the expectation of S was lambda M1, variance of S was lambda M2, right? And this is essentially what we're going to use here. So it's just another shortcut. But again, you can also use the whole formula and you will still get the same answer. So it will just be 10 times the value that we have now derived. And again, I think the question asks you to figure out the skewness as well, but it's going to be the same. So instead of putting squares for here, you will have to put cubes and then you will figure out the expectation of x cube, right? And skewness will also just be then multiplied by 10, and that will give you the answer, right? So to figure out the skewness of SI, it will just again be, maybe I can just write it here. So for skewness of SI, again, it will just be lambda times expectation of yi cube. And I guess this you guys can easily derive. And if someone would like a practice of it, the answer for this comes out to be 16384000000. But again, we really do not care about this stuff. It's just the same thing over and over again. Okay, so now we have our expectation of SI, we have variance of SI, right? Now we care about SR. So let us shift our focus from the insurance company to the reinsurance company now. So what do I have? I want to figure out expectation of SR now. How can I do that? Anyone? So first of all, we should try to define our SR, right? How do I define my SR? Anyone?
Z1 plus Z2 up till Zn.
Z1 plus Z2. And again, you know, the best thing to do is instead of using Z, let us just directly use W, right? So what I'm going to write is W1 plus W2, and this will go up until W NR. So you can also write Z1 as well. But again, we'll have to eventually convert it to NR, right? So that it is of practical use to us. So, okay, we have this. And now I want to figure out my expectation of SR. So what should I do? Anyone?
Expectation of NR into expectation of W.
Yeah. So it would be expectation of NR times expectation of W. All right. And what do you remember of NR?
That NR
So
follows Poisson with lambda pi.
NR follows Poisson with lambda pi. But do we know the value of pi here?
Oh, no.
That's the issue now, right? Is there something else that we can do? We do not know the value of pi. Otherwise, that would have been really convenient as well. But is there something else that we can do?
We can figure that out, that we have probably distribution of x and we know n, so we can figure out pi.
Can you be a bit clearer? Is this you're on the right track?
One, like we have defined pi as probability of x greater than n. So we know the distribution of x, and like it is basically 1 minus f of n. So it will be 400 upon 2000. Pi.
Yes. So yeah, that's actually really good. So what do we have here as pi? So what Saudi said was, what is my pi? Pi is just the probability that my x is greater than m, right? And my m here is what? 1600. And we have just derived that this amounts to 0.2, right? Do you guys agree with what I have written on the board? Hello. Do I have you all?
Yes, ma'am.
So, okay, so let me maybe go back. That was really good, Savi. So what do we have here? What was it? Yeah, here, right? So what was my pi? So, okay, first of all, we did know that my NR follows Poisson distribution with lambda pi, but we aren't given the value of pi here, right? So we look back and we see what is my pi. The way I have defined pi is that it is the probability that my x will take a value which is higher than the retention limit here, and this value for the sum that I am solving right now is what? It's 0.2, right? So I've just substituted that here, and that is how you get to know the value of pi here. Does this make some sense to you guys? So what will be my distribution for NR now? It will follow POSVA with the parameter. It has parameter lambda pi, right? And lambda pi is what? Lambda is 10. And what is my pi? 0.2. So it comes out to be 2. So I know that my NR follows POSVA distribution with the parameter 2. So if I know this, what can I conclude about SR? Anyone? What distribution will my SR follow if my NR follows POSVA distribution with the parameter 2?
Compound pose.
It will follow compound POSVA, right? With the parameter 2 again, right? Lambda remains same. So we have this thing now. Okay. But again, so okay, we did all of this stuff, well and good. But we also have to derive expectation of SR, right? So now do we know the expectation of NR? Yes, because we know its distribution for once and all. But we also need expectation of W. So what can I do with W now? So I need yes.
Ma'am, as we have seen that SR will follow compound Poisson with 2, then expectation of SR won't that be 2 itself?
Oh, okay, wait. So there's a difference between compound POSVA and POSVA, right? So if you have POSVA distribution, what is its mean? The parameter itself. But if you have compound POSVA distribution, which is S, what was its mean? Its mean was expectation of N times the expectation of X that you're summing up. Because remember, this NR is a random variable. It is not a known value to you, right? So it's not any POSVA distribution. It's a compound POSVA distribution where my W is a continuous random variable and my NR is a discrete random variable. But that was a really good question, I would say. So again, you have to be mindful, okay? If we have POSVA distribution, my mean and variance is the parameter itself. But if I'm looking at compound POSVA distribution, my expectation of SR is expectation of N times expectation of X. And here, so, okay, that was the expectation of S. And because we're looking at expectation of SR, and the way we have defined SR is in such a manner, we write expectation of SR to be expectation of NR times the expectation of W, which is what I've written there. Are things a bit more clearer now?
Yes, yes.
Okay, good. So what can I do next? I have to figure out my W as well, right? So how will I figure out expectation of W? For that, do I need to figure out the distribution of W first? So this is, yes, go on.
If we can use the earlier formula, then it is directly the expected value of Z upon probability of X greater than N.
Yeah, so if I have to write my G of W, what was it? It was f of X at W plus M upon 1 minus f of M, right? So what will this be? This is basically my f of X. What is my W here? I'm just gonna write a small w, but my M is 1600 upon, and this value is 0.2, which we have calculated ample number of times up until now, right? Okay, so what will be my value of f of X at W plus 16,000? Anyone? So remember, we are looking at f of x, and what is my x? My x follows a uniform distribution, right? From 0 to 2000. So what is my f of x here for this guy? So, okay, I guess we did define our f of x, right? Which takes a constant value everywhere. It does not depend on the value of x, right? So let's say if you're looking at Poisson distribution, or let's say exponential distribution, you know that your f of x is what? It's lambda times e raised to minus lambda x. So it varies with respect to whatever value your x takes, right? But what's happening here? We have a uniform distribution. And for uniform distribution, we know that irrespective of the value that my x variable takes, my f of x is always going to be 0.0005, but only within the range of 0 and 2000. Rest of the times, it's going to be 0. And for the other times, it's going to be 0.0005. Does this make sense to everyone? So try to see the kind of reasoning that I'm using. Again, these sums can take a bit of a time, and it's very easy to lose track of what we were trying to figure out and what we are doing right now. But if you go step by step, trust me, it really will be very simple and straightforward. I mean, I know it's easier for me to say, and it's another thing to do it on your own. But again, so I had to figure out expectation of W. And I know that for expectation, I first need this distribution. So I was looking if I know something about distribution of W. And I recalled that, yes, I have one formula for distribution of W. And now I'm trying to see whether I can use that to figure out the expectation of W. But I'm stuck here. I have to figure out the value of f of x at W plus 1600. And I just saw that my x random variable follows uniform distribution, right? So for every time this value here, okay, so let me maybe write it like this. So every time this value here, basically W plus 1600 is going to be between 2000 and 0. I know that my f of x, and then it could be any x. I mean, so again, what is my W here? W is the claim to the reinsurance company. So the another condition that we have for W is that it has to be greater than 0 always, right? Because it is the claim amount for the reinsurance company. So keeping this in mind, we now have this condition, and if this happens, then my f of x takes what value? What should I write here?
One by 2000.
Exactly, Prajakta. So it will be 0.0005, which is just 1 by 2000, right? So what I will do here is I will put a limit. So, okay, I had my W plus 16,000, which should be between 0 and 2000. So I'll maybe first try to rearrange this thing. So what do I get? I'll subtract 16,000 from everywhere. So I'll get minus 16,000 here. Of which W should always be greater than, and it should be less than 2000 minus 1600, which is just 400. And here I have a W, right? So now the conditions that my W should satisfy is 1 this and 2 this. And both of these conditions should always be satisfied. So what do I get at the end is I take the intersection of these two guys. So let us say this is my number line and this is my 0, and this is where my 1600 lies, and let's say this is where my 400 lies. So this guy says that my W should lie from here till here. Okay, but this guy says that my W should lie only from here till here. So what is my intersection? It is this area, right? So what do I get? That my W should always be greater than 0 and less than 400. Is this clear to everyone? Does this make sense?
Yes, ma'am.
All right. What about others? So do you see what I have done? So I know that my f of x takes 0.0005 value only if my x is between 0 and 2000, right? Otherwise it takes the value of 0. This is clear to everyone? So now what I'm looking at here is f of x w plus 1600. So what I did was, rest of the times it's going to be 0, but only for the times when this guy is between 0 and 2000, my f of x will take this particular value. Otherwise, it's going to be 0. And 0 upon 0.2 is just 0, right? So it's not really going to add up to anything. So what I'm going to do is, now I have defined a interval of w for which I will have a positive value of f of x, right? And not any positive value. It is always going to be 0.0005, right? Because that is what my f of x always takes. If any one of you haven't yet understand this, please ask me again and I will explain it again. Because this is a bit trickier and it might take some time to understand. But again, it's really not difficult and it's really easy as well. So once you get it, you're going to be really happy about it. Can I have a yes if you have understood and no if you haven't understood anything? And please tell me what part you haven't understood here.
Understood.
Yeah.
Yes, ma'am, understood.
Yes, ma'am.
Everyone? Okay,
Understood, ma'am.
so yeah, good. So now we know that my g of w, which is, I mean, I've just written g for the sake of being clear, but it's basically saying you the probability that your w takes the value small w is always going to be 0.025, right? So what is this? What does this say to you about w? If my probability that w takes any value is same throughout for this interval only, what can you say about the distribution of w? I'm using this and I'm using this. To figure out my w. Anyone?
Uniform distribution.
Uniform distribution on what parameters? On what values?
0 to 4.
Exactly. Very good. It will be from 0 till 400, right? Does everyone understand this? So because my probability that W will take any value is just same, only for this interval, I can say that my W is actually uniformly distributed over 0 and 400. Okay, so now I do know the distribution of W, which is what? Uniform 0, 400, right? And you also know the distribution of NR, which is Poisson lambda pi, basically Poisson with 2. So I guess it's really straightforward. What will be my expectation of NR? 2. My expectation of W, 400 upon 2, right? So it's just going to be 200. And thus I get that my expectation of SR is nothing but 400. And I think now it's really straightforward to even figure out the variance of SR and everything else, right? Is this clear to everyone? So again, another slick trick that you could have used was the fact that, so could have also used the fact that expectation of S is nothing but expectation of SI plus expectation of SR, right? So you know expectation of S and you know expectation of SI. This was just going to be expectation of N times expectation of X, and this you figured out times expectation of N, and you could have just subtracted this from this and you could have easily gotten the answer for expectation of SR. So what was this? This was, I guess, 1000. Was it 1000? No, it was 1000 times 10. So it was 10,000. And what was this? It was something 9600. Yeah. So you would essentially get the same answer, 400, right? So again, this would give you expectation of SR as 400. So this would have just been very easier. But again, to figure out variance and everything else, then you would have to struggle. But I guess I think you guys should take that as your homework. So what you have to figure out is variance of SR. And just to cross verify, its answer is 106667. Okay, that is the answer. And yeah, I would say that's it. That's all for today. Do you guys have any doubts, any questions, any queries up until now? Anyone?
No, ma'am, thank you.
Thank you, Risha. What about others?
No, ma'am.
No.
So I
No,
think
ma'am.
today's session was a bit heavier on the technical side. So let's have no class tomorrow, and maybe you guys can go through this sum and all the things that we have yet done, because I know it could be really confusing with starting off with simple things, simple random variables, adding them up to compound. Then we also had a look at sum of compound distributions. And then now we have reinsurance in place. So we had proportional, which was really easy. But if we have excess of loss and there is compound distribution, then we have to figure out for the reinsurance company, we take another random variable NR, and then we define a dummy random variable indicator function, which is I. And there are just so many distributions going on. Some compound pos one, some pos one, some simple random variables. So I think it's just a matter of 1 or 2 revisions. And if you guys do that, then you would be really good to go with this chapter, I would say. And I guess tomorrow we'll have, not tomorrow, in the next lecture, we'll have a look at the individual risk models. So that's a bit easier, right? Because what you will have is, so n won't be a random variable anymore. It will be known to you. So it's super easy. Nothing complicated will be going on over there. And I guess that's all from my side for today. Enjoy the rest of the weekend. And do revise, do study well as well. So we're covering things nicely, I guess. We're going at a good speed, I would say. Anything else anyone else would want to ask?
No, ma'am. Thank you.
Thank you. Thank you,
Thank you,
everyone.
ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.